Hello, my name is Rob Reynolds. Welcome to Business Calculus, Chapter 3, Section 3. Today we're going to learn about how to find concavity for functions, which is if the second derivative is less than 0, then it's concave down. If the second derivative is greater than 0, then it's concave up. We're going to discuss that here. Here's concave up, so that's if it's positive, if the second derivative is positive, and then concave down, like a frown, and that's if the second derivative is negative. That's different than the second derivative test. The second derivative tells you about concavity, but the second derivative test tells me about this, maxes and mins, just like the first derivative test told me about maxes and mins. It's just the second derivative test says you don't have to go through the first derivative, you don't have to go through intervals of increase and decrease like we did for the first derivative test to determine maxes and mins. There's an easier way to determine maxes and mins, and that's by finding the second derivative. So there's two different concepts here that we're going to be exploring. Once you determine that something moves from concave up to concave down, so here's maybe concave up, and then here's maybe some function that's concave down. You can see that it's kind of switching. Right there is called the point of inflection, where concavity is changing from either concave up to down or down to up. And we're going to be using the second derivative to find the maxes and mins. That is the second derivative test, which is different than finding concave up or concave down just using the second derivative. So don't get those two things confused. And then lastly, we're going to talk about points of diminishing returns. So again, once again, the right here, this area right here is concave up, and then this area in green over here is concave down, and this point right here is called the point of inflection, where concavity is changing. This slide is just saying, instead of talking about whether the function's increasing or decreasing, we're just going to look at the function curving using the second derivative and talk about its concavity. So check it out. This whole thing is concave down, but we're increasing on the left side, concave down, and decreasing on the right, still concave down. So to bring this to life to you here, the first derivative on the left, since this is decreasing, we know the first derivative is less than 0, but it's concave up, and concave up means that the second derivative is greater than 0. Over here, if it's increasing, then the first derivative is greater than 0, but it's still concave up. Second derivative is also greater than 0. So we're going to be looking for and discussing intervals of increase and decrease, even though we're talking about the second derivative concavity. The slide just says if it's concave up, notice that the tangent line are below, or the curve is above, and then if it's concave down, then the tangent lines are above, or like this says, the curve is below the tangent lines. So either way you want to think about that. So once again, if the second derivative is greater than 0, then it's concave up. If the second derivative is less than 0, then it's concave down. Just like we did for the first derivative, we're going to find these critical values again, but this time the critical values are where the second derivative equal to 0, or the second derivative is undefined. And the critical values are going to tell us intervals of increase and decrease. It's going to talk to me about concavity, and then where concavity changes, that's going to be a point of inflection. Let's try an example. You could do high d low minus, or low d high minus high d low for this problem, but the easier way is just to do a rewrite and write this as x squared plus 3 to the negative first, and then maybe a little chain rule, which says take the derivative of the outside, write down the inside, don't forget to decrease the exponent by 1, times the derivative of the inside. So I'm going to say that the first derivative here is negative 12x x squared plus 3 to the negative second. So that's the first derivative, and I could find critical values now, but let's go ahead and find the second derivative before we find critical values. So the second derivative says take the derivative of the first derivative, and I see this is the product rule, so we can't do what we did before. You can't just take the chain rule here, although we do have a little bit of chain rule happening here, but I see two functions. So I'm going to do the 1d2 plus 2d1 rule. And when I do d2, and here's where the chain rule gets applied. This is -3 times the derivative of the inside. So this is 1d2 plus 2d1. And I'll clean this up. Oh my goodness. Why didn't I pick an easier problem for my first example? And then factored form is usually the easiest form to look at this. So I'm going to pull out this x squared plus 3 to the -3rd, which literally means I'm going to think about dividing each term by that GCF. So if I divide by this guy, this term drops out, leaving me with just the 48x squared minus 12 times one of those, because if I have x to the -2nd over x to the -3rd, that really just becomes rewrite the base and subtract. So -2 minus a -3 just becomes a 1. So that's why I have one of these left here. So critical values. Well, let's combine some like terms and then throw this back in the denominator. So the second derivative can be simplified as 36x squared minus 1, which will be easier to find the critical values in this form. So the simplified form, see, now I can see critical values here are plus or minus 1 from the numerator. And this never equals 0. So my intervals are going to be from -infinity to the first critical value, -1 to 1, and then 1 to 1, 1 to infinity, just like we did before for the first derivative test. So this time, though, I'm testing the second derivative, so I'm going to test a value like, I'll use like -2, anything in that interval, 0 and then 2. So f double prime -2, since that is going to be positive, my conclusion is concave up. And f double prime 0, which means go to the second derivative and plug in a 0. So if I plug a 0 into this guy right here, that's going to be negative, which means it's concave down. And then f double prime 2 is going to be greater than 0. Again, that's positive, and that's going to be back to concave up. So if the direction is just asked for concavity, I've located there's the same derivative that we had, and so good. So if they're only asking for concavity, then we're done. If they would have asked for points of inflection, then I would have said, the point of inflection is at these right there at -1, because it switches from concave up to concave down, and there's another point of inflection right here because it went from concave down to concave up. So there must be a point of inflection at 1 and at -1, those critical values, which I can see there really is a. So here's kind of concave up, here's kind of concave up-ish, and then this is more concave down, and you can see there's points of inflection at those values. So again, at the turning point where it moves from concave down to concave up or vice versa. So I do the exact same thing for points of inflection. I got to look for concavity to change. And that might even happen where the slope is undefined, where it's a vertical line. So the tangent vertical line for the third one, slope doesn't even exist, but there is a point of inflection. So there's some definitions about that. You're welcome to read through those. I'm going kind of fast because I'd rather get to the examples. So again, equal to 0 or undefined, just like the first derivative as well. So here we go. Example number 4. To find points of inflection, I'm going to go for the second derivative. Well, and first I'll have to find the first derivative, 4x cubed plus 3x squared minus 6x. The second derivative is easy enough to find. The 3 times the 4 is 12. X squared plus 6x minus 6. Of course, I could factor out a 6. 2x squared plus x minus 1. Set that equal to 0. 6 never equals 0, so throw it away. And this will factor nicely to 2x minus 1 and x plus 1. Work on your factoring skills. So the critical values are 1/2 and 1. And then I would either do the chart, or if you wanted just to slap down a 1/2 and a 1 for the critical values and run your test. throw in a 0 perhaps, something between 1/2 and 1, maybe as a 3/4, and then f double prime 2, and start checking for these to be greater. Let's throw in the 0 together. If I throw a 0 into this guy right here, this first guy goes negative, and the second guy goes positive, which means that's negative or less than 0, and then that's concave down. And then I repeat this process for those. So checking the graph of this really quick, I can see I did something wrong because I can see that it should have been concave up. And what I did wrong was I dropped this negative right here, which means my number line, good grief, should have looked like this. -1 is here and the 1/2 is here. So now when I check the f double prime 0, which I did before, it's still less than 0. I did all that right. So this is concave down here, but I should have been checking something like f double prime -2. And if I plug the -2 in here, this is negative and negative, which makes that greater than 0, which means this is what's concave up. So this is switching from concave up to concave down, so I've located one point of inflection, and sure enough, this, if you plug in something higher than 1/2, like even a 1 would work, this is going to be concave up again, and that'll be another point of inflection. So I apologize, went too fast. So there's my intervals, and you can see this is concave up on here and here, and then this interval is concave down. So your conclusion is, sure enough, you've got a couple points of inflection here and here. You can see concavities changing there. So the second derivative test I talked to you a little bit about. The second derivative test is not talking about concavity like the second derivative, and it's not talking about points of inflection like the second derivative. But when I add this word test, then I want you to think, well, that's the same thing as the first derivative test, or at least it finds the same thing as the first derivative test. Maxes and mins is what we're talking about now. But the second derivative test says really just take the critical values from the first derivative, plug them into the second derivative, and then if it's greater than 0, then that means, yes, it is concave up, which means you've located a minimum. How come? Well, if it's concave up, then you know that there's a minimum right here. So you're actually finding the critical values from the first derivative and plugging them into the second derivative. That's the second derivative test. Here's a nice little illustration about how to graph. Here's a cubic function, and the derivative of an x cubed is an x squared. So you can see here's the slope of 0, and that's why it hits this function here. So the red has a slope of 0 here and another slope of 0 here. So if you were to graph the derivative, it'd be here. And notice that the slope is really steep, and that's why it's up high here, but it's getting closer and closer to 0. So it's coming down, getting closer and closer to 0. And then down here, when it turns a corner here, the slope is actually negative, so that's why you're below. So down here, the derivative is negative, below 0, and that's why the function is below until it hits here, and the function has a slope of 0 here, and that's why this point is here, and then it's still close to 0, but then it's really increasing really fast, and that's why this is increasing real fast. And so hopefully, given a function, you can talk to me about what its derivative, the graph of the derivative, looks like. So the second derivative test, again, take the critical values from the first derivative, plug them into the second derivative to determine maxes and mins. I'll give you an example. The first derivative for this given function is negative 15x to the fourth plus 15x squared. And if I factor out a negative 15x squared, I can find critical values pretty easily, and there's a lot of them. If I set them equal to 0, critical values are 0 and plus or minus 1. So I'm going to now find the second derivative and plug those three critical values into the second derivative. Let's go find that second derivative using this guy right here. The second derivative is negative 60x cubed plus 30x. So then if I factor out a negative 30x, I'm left with 2x squared minus 1. So there's my second derivative, which I'm going to plug in different values, the critical values. So I'm going to start with -1, and then I'll move to the next critical value, which was a 0, and then let's plug in a 1. And so if I plug a -1 into right here, all I really need to do is determine if it's positive or negative, so I don't worry about the actual value. But -1 times -30 is positive, and then this guy right here is going to be positive. And so this is greater than 0. So then I know that it's concave up. Oh, my pin's not working. And if it's concave up, that forms a minimum. So now I've just determined that there's a minimum at -1 comma something. So continuing this, I'll throw a 0 in. That makes this term 0, which is just 0. 0 is neither positive nor negative, so I can't make any conclusions about this point. But then if I plug in a 1, I'll find out that this is negative, so it's concave down, and that's going to create a max. And the max is at 1, 0. So that's the second derivative test.